today let's prove the Fermat's last theorem when n equals 4, and we know that is x to the 4 plus y to the 4 equals z to the 4, and x, y, z need to be all natural numbers. So, and I learned another two methods to prove it. And we know because based on the last video, we know that is we just need to prove x to the 4 plus y to the 4 equals z to the 2, because we're going to prove this equation is a false statement when x, y, and z need to be all natural numbers. So we only need to prove x to the 4 plus y to the 4 equals z to the 2 is a false statement when x, y, z are all natural numbers. So I have two methods. So the first method is first I just say we have a root. I just mean we have a solution. Is x, y, and z. It's x, y, z. We have this solution, and we set, of course, p is the divisor of x. Sorry, p is a odd prime, and p is the divisor of x, and p is the divisor of y. And so that tells us p to the 4 is the divisor of x to the 4 plus y to the 4. Because p to the 4 is the divisor of x to the 4, and p to the 4 is the divisor of y to the 4. So p to the 4 is the divisor of x to the 4 plus y to the 4. So that's equal to z to the 2. So that tells us p to the 4 is equal to, p to the 4 is the divisor of z to the 2. So that tells us p to the 2 is the divisor of z. Right, okay, so if you notice this, so that means what? X divide P, and Y divide P, and Z divide P squared is also a solution. So, okay, so proceeding this manner, we can find a solution with x and y are relatively prime. So that means, so I just said that solution is x, y, and z. Okay, so let's write. Greatest common divisor of x and y is equal to 1. So for this, so these two things, this problem, this part of proof, it is using from both of these two methods. So, and another proof is the same. It's use of both of these two methods. So is using on both of these two methods. So first, we know because x and y need to be relatively prime, so if x and y are both even, they're not relatively prime, so we don't need to care about it. But if x and y are both odd numbers, so what will happen? Let's just see. X to the 4 plus y to the 4, what will happen? Because odd number square, we proved in the last video, is odd numbers. The square of an odd number, it is congruent to 1 mod 4, so that's an odd number, right? The square of an odd number is an odd number. So this, and with the square of this odd number, it is still congruent to 1 mod 4. So we know odd number to the 4 is congruent 1 mod 4. So x to the 4 is congruent to 1 mod 4, and y to the 4 is congruent to 1 mod 4. So that is congruent to 1 plus 1, and that is congruent to 2, and that's congruent to z squared. So, and then mod 4. So what we need to do now is, let's see, a perfect square, because because z to the 2 is a perfect square, and we know a perfect square, that's a square of an even number, so that should be congruent to 0 mod 4. If that's an odd number, a square of an odd number, that should be congruent to 1 mod 4. So now z to the 2 is congruent to 2 mod 4. So none of those perfect squares are like this, right? So z to the 2 is not a perfect square. So that's not right. So only could be x and y need to be opposite parity. So everything now is done. So we just, these two things that we have already proved. So we could set x is equal to odd, and y is equal to even, and z is equal to odd. What's now? So now we can find a solution is x to the 2 and y to the 2 and z, right? So if we have a solution, so we can write out, this is a primitive Pythagorean triple. Okay, so x to the 2 is equal to m squared minus n squared, and y to the 2 is equal to 2mn, and the z is equal to m squared plus n squared. So we can change the first equation to y, let's see. We can move this to the left part. So x, we can move this to the left part, right? So x squared plus n squared is equal to m squared. So that's another primitive Pythagorean triple. So let's write out this x is equal to r squared minus s squared, and n is equal to 2rs, and m is equal to r squared plus s squared. So now what we're going to do is, we know m times n divide 2 is equal to 2mn divide 4, and that's equal to y squared divide 4. So that's equal to bracket y divide 2 bracket square. So that, and we can set, let's let me make it up here. So okay. Okay, and we know m, and so we can set m is equal to odd, and n is equal to even. they need to be relatively prime. So, right? So, if they need to be relatively prime, so n is even, so what we can get is, what we have is n is even, so odd number don't have, m, right? M is an odd number, so an odd number didn't have a factor 2. So n is even, so n and n is even, m is odd, and there they are relatively prime. So they're relatively prime. So m and n divided 2 are relatively prime too. So these two guys are the square from this. So they're perfect square, and another thing we know is RS is equal to n divided 2. RS is equal to n divided 2. So let's see. Let's go to n divided 2, and then so R and, because the corresponding divisor of R and S are equal to 1. So because R and S are relatively prime, and R and S are relatively prime, and n divided 2 is a perfect square, so R and S are perfect squares. So now we know M are a perfect square. So perfect square. So let's see. So we can set R is equal to x3, x1 2, and S is equal to y1 2, and M is equal to z1 2. So the last step, of course we are almost done in the first method, using the first method. Of course we can plug these guys in here in this last equation, so we can get what we have is x1 2 and plus y1 2, x1 to the 4th plus y1 to the 4th, and that's equal to z1 to the 2. So let's see. So here, so we got another solution of this equation. So so we know z1 right here, okay? Z1 it is z1 to the 4 is less than z1 to the 4 plus n squared. And that's equal to m squared plus n squared, and that's equal to z. So we know, so that tells us, that give us z1 to the 4, it is less than z. So that gives us z1 is less than z. So this creates a contradiction, because of course we know in this part of proof, we know because we take x, y, z to be natural numbers. So we can take all of the solution, z parts of all of the solutions, so that creates a subset of natural numbers. And all subsets of natural numbers are bounded below by Lagrangian principle. So what we'll do is what we'll do is to take their z parts from that set and then take the middle one. So that means z is the minimum z parts, right? And z1 is in the same subset. Z is in the subset, z part subset, and z1 is in that same subset. So that creates a contradiction because z is a minimal value, the minimal z parts in that subset, but z1 is less than z, so that's a contradiction. So now I'm gonna clean this part backward and let's start the next part. Now let's start the second proof. Okay, so now let's prove the second proof. Now let's get the second proof. But of course, you know the first proof is a little bit. It is a little bit similar with the proof, the method of the last video, because that two methods are both using the primitive Pythagorean triple, but the second method did not use that primitive Pythagorean triple. No. So let's keep going on. First, we know we can move the x to the fourth to the move the x to the fourth to the right. So y to the 4 is y to the 4 is equal to z to the 2 minus x to the 4. So that's equal to bracket z minus x to the 2 and bracket times z and times bracket z plus x squared in bracket. So we have it. Now, so we set p is the divisor of z plus x to the 2, and p is the divisor of z minus x to the 2. So p is the divisor of the sum of these two parts. So p is the divisor of 2z because and we set p is a odd prime, right? P is an odd prime. So p is an odd prime. So if p is the divisor of 2z, so that means p is the divisor of z. So what we do now is p is the divisor. Of course, p is the divisor of these two parts, the difference of these two parts. So p is the divisor of 2x squared. So that tells us p is the divisor. Sorry, here is that tells us, right? And that tells us p is the divisor of x to 2. And that tells us what? Because p is a prime. So if p is the divisor of x to 2, that means p is the divisor of x. So that tells us p is the divisor of x. So what we do now is actually we can prove if p is the divisor of z and p is the divisor of x, so p is the divisor of y. Why? Why is that? Because we can set x is equal to Pn and z is equal to Pn. So if we plug in our original function right here, so we can have y to the 4 is equal to we can factor out p to the 2. So p to the 2 I can call it p squared. P squared times bracket n to the 2 minus p to the 2 times n to the 4. So now we're going to do bracket, right? Okay. So that means p to the 2 is the divisor of y to the 4. So p is the divisor of y squared. So because it's the same reason that we talk about y, we can prove p when p is divisor of x squared, so p is divisor of x because p is a prime. So right? So p, that tells us p is the divisor of y. So now you prove p is the divisor of y, so that contradictions because that was contradiction with the greater common divisor of x, y is equal to 1. So why is that? Because we know p is the divisor of x, right? And p is the divisor of y. So the greatest common divisor in this case, the greatest common divisor of in this case, the greatest common divisor of x and y is greater or equal to b. So that has a contradiction. So what we do next step is right. So we prove p cannot be a odd prime. So let's see if that's a even number. It's an even number. So we can prove these two guys only can be a multiple of 2. But if that's a multiple, if these two guys are both multiple of 4, what will happen is, let's think. I said z plus x to the 2 is congruent to 0 mod 4. Okay. So then we have what? Because we know x is even. Of course I forget. Yeah. X is odd. Sorry, x is odd. So if x is odd, so we talked about that in the last video. The square of an odd number is congruent to 1 mod 4. So right. So that means z is congruent to -1 mod 4. So we know that tells us c minus x squared it is congruent to mod 4. Why is that? Because this is congruent to 0 and this is congruent to 1 and -1. So what we do is just, of course, because for calculating this, we can use z to minus x to the 2, so x squared. So that's -1 minus 1. So that's -2. So that's mod 4. We can change it to 2, right? So now we have this. That means that tells us z plus x to the 2 is multiple of 4, but z minus x to the 2 is not a multiple of 4. So actually, because you will find out if we all of the even numbers except 2, you'll find out because z is always congruent to -1 every time. You see mod anyway, mod 6, mod 6, mod 8, mod 10, like that, always. And like here, you are just calculating it. Of course, it is always not 0, right? So that means that tells us z plus x to the 2 and z minus x to the 2, they're not relative. Their greatest common divisor, the greatest common divisor of z plus x squared and z minus x squared is equal to what? Is equal to 2. So now we have two cases. case one is z minus x to the 2 it is equal to 2a to the 4 and a need to be equal to odd. Because if a is even, so this part will be a multiple of 4. It's a multiple of 4. So that's not right. Because another part is 8 times b to the 4. So only can be one of them is even. And a is greater than 0. So and z plus x to the 2 it is equal to 8b to the 4, 8 times b to the 4. And we can prove a case 1 is impossible because we know if we use this to minus this, we can get 8 times b to the 4 minus 2a to the 4. We know this minus this is 2x squared. So 2x squared is equal to this minus this, so we can cancel out the 2, so that means x to the x squared is equal to 4b to the 4 plus a to the 4. So what's now? So and we know this part is congruent to -1 if that's mod 4. You know why? Because this part, because 4b to the 4 must be a multiple. It must be a multiple of 4. So this part is congruent 0 mod 4. But let's see. Sorry, it is minus. And this part, I mean negative a to the 4, because a is the odd number. So that's an odd number square is an odd number, and an odd number to the 2, and an odd number square, and a square of that odd number again. So that's a multiple. That's a congruent 1 mod 4. So that means that tells us negative a to the 4. That means a to the 4 is congruent 1 mod 4. So negative a to the 4 is congruent negative 1 mod 4. But x to the 2 is congruent 1 mod 4. So actually this, because x to the square 2, this part is equal to this part, but they're not congruent to the same remainder than mod 4. So that is a contradiction, because x to the 2 is equal to 4b to the 4 minus a to the 4. But 4b to the 4 minus a to the 4 is congruent with negative 1 mod 4. But x to the 2 is congruent with 1 mod 4. So that create a contradiction. So case 1 is impossible. So of course we know that has a case 2, right? Case 2. So case 2 is z plus x squared is equal to 2a to the 4, and a is equal to odd. A is greater than 0. So and z plus z minus x to the 2 is equal to 8b to the 4. And right, so this is case 2. Case 2 is right. Case 2 it didn't create a contradiction. So let's keep going on. What we're gonna do is case 2. Case 2 is z plus x to the 2 plus z minus x to the 2. So of course that's equal to 2z, and that's equal to 2a to the 4 plus 8 times b to the 8b to the 4. So now we can change it to z is equal to a to the 4 plus 4b to the 4. So that means z. Sorry. Yeah. A is greater than 0 and a is greater than 0 is less than a is less than z. So let's see. So now we are almost done. So first z plus x to the 2, and then minus bracket z minus x to the 2, and that's equal to let's see here. It is equal to 2x to the 2, and right, it's equal to 2x to the 2, and that's equal to 2a to the 4, and then plus 4b to the 4. So now that means 8 times b to the 4. So x to the 2 is equal to a to the 4. Sorry, I got it wrong. It's minus 4b to the 4. So if we move this part to here, this part to the left, and this part to the right, so we have 4b to the 4 is equal to x to the 2. It is a to the 4 minus x to the 2. So that is equal to bracket a to the 2 minus x, and then times bracket a to the 2 plus x. Bracket. So right here, let's see. So using this part of the proof, at the same way you can try to prove this too. Actually, they're the same. You'll find out you still can prove the greatest common divisor of a squared minus x and a squared plus x. So now, and that's equal to 2. Right now, we can set. So that means we can set what? we can set a squared minus x is equal to 2c squared, and a squared plus x is equal to 2d squared. So if we plus them, these two guys, if we plus them together, we can get 2a squared. 2a squared is equal to 2c squared plus 2d squared. So that tells us a to the 2 is equal to, it is equal to what? 2c squared. Is equal to c squared plus d squared. So now we can, here I read it wrong, because it should be to the 4, right? Because don't forget, here is 4b to the 4. So it should be c to the 4 and it should be d to the 4. Here's c to the 4. To the 4, c to the 4, d to the 4. So that creates a contradiction now, because this is another solution of the original function. So we need to check about this function, and we check about this function and this equation and the original function, right? This function and this equation and the original function. So these three functions create a contradiction, because we know z is a minimum value, right? Z is from the first proof right here, we prove that z is the minimum z part in that subset, and a is in that same subset. So a when we prove a is less than z, right? A is less than z, and a is in that same subset where z are. A is in that subset where z are. So, and z is the minimum z part in the subset, so that creates a contradiction, because actually a is that z part too. Okay, so that means that creates a contradiction. So we proved x to the 4 plus y to the 4 equals z to the 2 is a false statement when x, y, and z need to be all natural numbers. So that means we also proved x to the 4 plus y to the 4 equals z to the 4. It is a false statement when x, y, and z need to be all natural numbers. So now we prove this problem using two different methods.